State the law of conservation of angular momentum. Now, this law is very similar to the conservation of linear momentum in that if there's no external force, the total linear momentum of a system will remain constant. So what we're going to do is we're going to take this definition and change a couple of words, namely the word linear to angular, and we're going to change forces to torques. Now, to secure that mark, you need to include the words angular and torque. If those are missing, then you won't get that mark. Figure 1 shows an orbiting satellite with two small instrument pods attached to the ends of telescopic arms. The arms can be extended or retracted by a motor in the body of the satellite. So we've got figure 1 there, as described, with an axis rotation at the center and then various masses at various radii from that center. With the telescopic arms fully extended, the center of mass of each instrument pod is at a radius of 4.1 meters from the axis of rotation. Moment of inertia of satellite body about axis equals 71 kilogram meters squared. The mass of each instrument pod is 5 kilograms. The mass of the telescopic arms is negligible. Show that the total moment of inertia of the satellite with the arms fully extended is 240 kilogram meters squared. For this question, we need to add the two moments of inertia together. So we're already given the moment of inertia of the satellite body. Let's write down a formula to show how we're going to combine this. So as you can see, we're adding those moments of inertia together. You'll notice here I've included that the 2mr squared represents the moment of inertia of both pods, so mr squared would be the moment of inertia of one pod. So all we need to do is substitute our values into this equation, and that will give us a value of 239 kilogram meters squared, which obviously rounds to 240 kilogram meters squared. So in terms of marks for this question, your first mark will be for clear use of the equation that I've written, I equals I body plus 2mr squared. And your second mark will be for getting the correct specific answer at the end, not the 240, but the 239. So 2 marks there. The satellite is initially rotating slowly about its axis with the arms fully extended. The arms are slowly retracted so that the instrument pods move closer to the body of the satellite. State and explain the change in the angular speed of the satellite as the arms are retracted. Now, the first thing we can say based on the equation that we wrote down before is that because the pods decrease in radius from the center, the term 2mr squared is going to get smaller, and therefore the overall moment of inertia is going to decrease. So we'll get our first mark for saying that. The second mark will be for backtracking through what I've written here in purple about the radius decreasing. So your second mark will be for saying this. You might want to just add some extra detail here to say that more of the mass is closer to the center. And that will secure your second mark. The third mark will be obtained for relating this change in moment of inertia to the angular momentum. So the equation that we need is this. So we can see here that moment of inertia and angular velocity are inversely proportional. So if the moment of inertia is decreasing, the angular velocity must be increasing because we're keeping the angular momentum constant, as we stated in a previous question. Now for this third mark, you need to say that the angular momentum stays constant and that the angular velocity will increase. If you miss either of those points, you won't get that third mark. So 3 marks there. The satellite is initially rotating at 1.3 radians per second with the telescopic arms fully extended. When fully retracted, the instrument pods are at a radius of 0.74 meters from the axis. The satellite contains sensitive equipment that may be damaged if the rotational speed exceeds 4.2 radians per second. Deduce whether the arms can be retracted fully without the satellite exceeding its maximum permitted angular speed. Now for this question, we need to apply the conservation of angular momentum. And here I'm saying that 1 represents the situation before the change, and 2 represents the situation after the change. So we need to apply our values to this equation. So we have an initial moment of inertia of 240 kg/m squared, as we saw before. We have an initial angular velocity of 1.3 radians per second, as stated in the question. So let's find out our initial angular momentum. So we have a value of 312 Newton-meter seconds. Newton-meter seconds is a unit of angular momentum. So our first mark will be for making this calculation. Our second mark will be for relating this to the angular momentum of the system after the change. So you can see here I've kept the same moment of inertia of the body because that stays constant. The mass of the pods remains the same at 5.0 kilograms, but you can see that the radius has now changed to 0.74 meters. We don't know the value of the angular velocity or the angular speed after the change because that's what we're trying to find. So we need to make a rearrangement here. And that gives us a value of 4.08 radians per second. Now you remember that the maximum possible rotational speed is 4.2 radians per second, and we are within this range, so the arms can be retracted fully. Our second mark will be for calculating the 4.08 radians per second, and then our third mark will be for making a concluding statement. So 3 marks there. State one function of a flywheel. So there are a number of functions that we can apply with a flywheel. We just need to write one of those down. So what we're going to write down is the smooth out rotational speed. And that's going to be our mark. Instead of rotational speed, we could say torque or power. But the other function of the flywheel is to store rotational kinetic energy. So either of those points will get you a mark. A student does an experiment to determine the frictional torque acting at the bearings of a steel flywheel. The flywheel has a radius of 0.075 meters and is perfectly balanced. The student places a small magnet of mass 0.020 kilograms at point A on the circumference of the flywheel on a horizontal line through the axis of rotation, as shown in figure 2A. The student releases the flywheel. The flywheel first comes to rest when it has moved through an angle of 3.00 radians, or 172 degrees, with the magnet now in position B, as shown in figure 2B. So we've got figure 2A and 2B there, with the flywheel as described, and the magnet in positions A and B. The loss in gravitational potential energy of the magnet equals the work done against the frictional torque acting at the bearings. Show that the frictional torque is about 7 times 10 to the power of minus 4 Newton meters. So for this question, we can see that A is released, the magnet swings down, but only reaches position B on the other side. So the work done by friction, in this case, is going to be equal to the torque multiplied by, so the loss of energy in this system is going to be equal to the difference in gravitational potential energy between this point and position B. So we're interested in finding the vertical difference between these points so that we can find the difference in gravitational potential energy. So let's do that first of all. So I've written 0.075 sine of 8 degrees, and that's because this triangle has a hypotenuse of length 0.075 meters and an opposite length of delta H. So we're going to say that sine of that 8 degrees is equal to delta H over 0.075. So that's where that comes from. So we end up with a value for delta H of 1.04 times 10 to the minus 2 meters. So the overall change in gravitational potential energy of the magnet is going to be equal to this change in height multiplied by the magnet's mass and then multiplied by the gravitational field strength of 9.81 newtons per kilogram. So let's write that down. So that's the difference in energy. What we can then say is that that difference in energy is equal to the work done against the frictional torque. And the frictional torque is calculated as the torque multiplied by the angle. So if we go back to our diagram, this torque has acted over the 172 degrees, or 3 radians, as described in the question. So we need to divide our energy difference by this angle in radians. And this gives us a value of 6.80 times 10 to the minus 4 Newton meters. Now, in terms of marks for this question, your first mark will be for correctly calculating the value of delta H. Your second mark will be for calculating the difference in gravitational potential energy of the magnet. And your third mark will be for calculating the exact value of the frictional torque. So 3 marks there. The student goes on to determine the moment of inertia of the flywheel. The magnet is removed and the flywheel is made to spin. Measurements show that the flywheel makes 573 rotations as its angular speed reduces uniformly from 25.0 radians per second to 0. Assume the frictional torque at the bearings is constant and the same as in question 2.2. Determine the moment of inertia of the flywheel about its axis of rotation. So for this question, we need to use the angular equivalent of a suvat. So the linear version of the suvat would look like this. So v squared equals u squared plus 2as. We need to use the angular equivalent. So this time we have angular velocities, angular accelerations, and then angular displacements. What you'll notice is that the initial and final angular velocity are given to us. It goes from 25 radians per second to 0. So omega f will be 0 and omega I will be 25. We can also convert the number of rotations, 573, into a number of radians to substitute in as theta. So by doing all of this, we can find the value of alpha, which is the angular acceleration. So let's rearrange this equation to make alpha the subject. So this will give us a negative value, but remember this wheel is slowing down. So we end up with minus 0.087 radians per second squared. Now our torque is going to be negative as well, because it's a decelerating torque. So our moment of inertia will be a positive number. So I've said here that moment of inertia is equal to torque divided by angular acceleration, in a similar manner to how mass is equal to resultant force divided by acceleration. Think of this as an angular equivalent of Newton's second law. So let's substitute in our values. So we end up with 7.82 times 10 to the minus 3 kilogram meters squared. So that's the value that we write into the answer space. In terms of marks for this question, there are a number of places that you can get those marks, and there are more opportunities to gain marks than there are marks available in the question. So let's look at the first. The first mark is for the use of the angular equivalent of v squared equals u squared plus 2as. The second mark is for correctly converting the number of rotations into a value in radians. The third mark will be for correctly calculating the angular acceleration. If the unit isn't included, you still get the mark. And another mark is possible for using the moment of inertia torque angular acceleration equation to calculate the correct answer. But remember, there's a maximum of 3 marks available here. So 3 marks there. Figure 3 shows the PV diagram for an idealized diesel engine cycle. In this cycle, a fixed mass of air is taken through 4 processes: 1, 2, 3, 4, and then 1. We've got figure 3 there with that cycle on a PV diagram, so pressure on the y-axis and volume on the x-axis. Which statement about this cycle is true? Tick the correct answer. So we have work is done by the air in process 4 to 1. Energy is supplied to the air by heating only in process 2 to 3. The temperature of the air rises in process 3 to 4. Or the area enclosed by the loop 1, 2, 3, 4, 1 is the power output of the cycle. Now the answer to this question is the second one. Energy is supplied to the air by heating only in process 2 to 3. Let's just look back at the diagram. Now there are two ways to supply energy to this system. One of those is heat and the other is work. We can see that this cycle is moving clockwise because it says 1, 2, 3, 4, 1. So it's going from 2 to 3. What this means is that the volume is expanding. So the gas is doing work. There is no energy being transferred to the gas through work. Otherwise it would be compressing, getting smaller. So the only way in this situation that energy is transferred to the air is by heating. Now you don't need to explain this for the question, but you need to tick the correct box, so that's your 1 mark. The cycle in figure 3 may be modified by allowing the air to continue to expand adiabatically from state 4 until it is at atmospheric pressure at state 5. Figure 4 shows the modified cycle. So you can see figure 4 there with that modified cycle, where it extends onto 5 into a point instead of that flat edge between 4 and 1. The expansion stroke 3 to 5 is now longer than the compression stroke 1 to 2. Process 5 to 1 takes place at constant pressure. It has been claimed that, compared to the cycle in figure 3, the modified cycle of figure 4 gives A, an increase in work done per cycle of 130 joules, and B, an increase in efficiency of more than 15%. Deduce whether these claims are true. And then we have an answer space for claim A and claim B. Looking first of all at claim A, where we have an increase in work done per cycle of 130 joules. Let's look at how much is added on the graph. Now we can see from this graph that each square represents 10 joules. So it has a height of 10 to the 5 pascals according to the scale on the y-axis. And the width will be 10 to the minus 4 meters cubed, which would be shown here as 0.1 times 10 to the minus 3 meters cubed, but it's the same thing. So let's multiply those together. So we end up with 10 joules because that's 10 to the power of 5 multiplied by 10 to the power of minus 4. Now looking at the shape 4, 5, 1, 4 is not quite a triangle because there's a curved edge there. This shape takes up approximately 9 squares, which is therefore 90 joules. So it's certainly not an extra energy per cycle of 130 joules. So let's put our answers into the answer space. So each square represents 10 joules. That's your first mark. Your second mark will be for not only saying that that extra area on the graph is 9 squares, but that it's also an increase of 90 joules. So there's your second mark. So claim A is untrue. We'll talk about the mark for this point a bit later on. So it's saying that claim B is that there's an increase in efficiency of more than 15%. Now the area of the original loop is 55 squares, which corresponds to 550 joules. This means that the new area of the overall loop 1, 2, 3, 4, 5, 1 is going to be 640 joules. So where we were dividing 550 joules by the input energy to find the efficiency, we're now dividing 640 joules by the same input energy to find the new efficiency. So the difference in efficiency is going to be our efficiency increase, and that's what we need to write down in the answer space for claim B. So the original efficiency is going to be 550 joules divided by the inputs. The new efficiency will be 640 joules divided by the inputs. So the change in efficiency is going to be the difference between the two, which is going to be equal to 90 joules divided by the input energy. So we want to work out what this efficiency increase is as a fraction of the original efficiency. So let's do this as a percentage increase. You'll notice here that whatever the input value is, it will cancel because there's one on the top and one on the bottom. So we just end up with 90 over 550. And that gives us 0.16 or 16%. Now going back to the original claim, it says an increase in efficiency of more than 15%. So claim B is true. Now in terms of marks for claim B, your first mark will be for correctly working out that you need to divide 90 by 550. Your second mark will be for correctly calculating the percentage change in efficiency. And then for your fifth mark for this question, you need to correctly state which claim is true and which claim is untrue. But you need a conclusion on both of these claims. So 5 marks there. The first law of thermodynamics can be written as Q equals delta U plus W. State the meaning of the terms Q and delta U in this equation. So very easy 2 marks here. We know that Q is related to heat and delta U is related to the change in internal energy. So we just need to write those down. So for saying the energy gained or lost from the system as heat, you'll get your first mark, but you need to reference energy there. You can't just say heat. And then delta U is the change in internal energy. You can say increase in internal energy or decrease if it's negative, but change is fine here. So just for sake of completion, I'm also going to say that W represents the work. So the work done on or by the system. So for example, in a body of gas, that could be through expansion or compression. So 2 marks there. For the air in process 5 to 1 in figure 4, delta U is equal to minus 374 joules. Calculate the energy that must be removed by cooling for process 5 to 1. So we can see process 5 to 1 here. So we're going from right to left. Now we're trying to calculate the heat energy, Q, and we're given the change in internal energy. So the odd one out here is the work. And the work done is represented by the area under the graph. So we're interested in this rectangle, which I've shaded underneath the line. So we've got a pressure there of 10 to the 5 pascals, and then a change in volume of 1.5 times 10 to the minus 3 meters cubed. And to calculate the work done, we just need to do P delta V, so multiply those together. So we'll do this in the answer space. So we end up with a value of 150 joules. Your first mark will be for making that calculation. Your second mark will be for using delta U and W to calculate Q. So we'll use the equation that we saw in the last question. So let's substitute in our values. So we end up with a value of minus 524 joules. We have minus 150 joules for the work here because there's a decrease in volume of the air. Now typically in this equation, Q is the heat added to the system. So because we have a minus value, that represents the system being cooled. So actually the energy removed will be 524 joules without the minus, because we have a negative value of heat being added, which means heat is being removed. So your second mark will be for calculating this value correctly. So 2 marks there. 0.060 moles of air is taken through the cycle. Determine the maximum temperature in the cycle. For this equation, if we're dealing with a number of moles of gas, we need to use the ideal gas equation. I'll just add some labels there. So we have pressure times volume is equal to the number of moles multiplied by the molar gas constant multiplied by the temperature in Kelvin. And it's really important there that that temperature is in Kelvin and not degrees Celsius. So let's go back to the graph to work out when that maximum temperature would take place. Now, if the temperature is at its maximum value, then the product of P and V must also be at its maximum value because we're saying that PV equals nRT. Since it's a fixed number of moles and the molar gas constant is just a constant number, as I said, when T is at its highest, PV must also be at its highest. And that point will be 0.3. So let's write that into the answer space along with the corresponding values of P and V. So let's write down those values of P and V. So the pressure will be 14.5 times 10 to the 5 pascals, or 1.45 times 10 to the 6 pascals. And then the volume will be 0.45 times 10 to the minus 3 meters cubed. That's not the highest the volume can be, but it's a value at which the product of that and the pressure is the highest. So let's now rearrange the ideal gas equation to make T the subject, and then substitute in our values. And that gives us a value of 1310 Kelvin. And we can write that into our answer space. So in terms of marks for this question, your first mark will be for the use of the ideal gas equation. Your second mark will be for noticing where the highest temperature will be, i.e. where the highest value of PV will be. And your third mark will be for calculating the correct answer. So 3 marks there. The national grid is supplied mainly from power stations which have overall efficiencies of up to about 40%. Table 1 shows the average power requirements of a large paper manufacturing business, a paper mill. So as you can see there, Table 1, different requirements, and then the power that those things require. The paper mill can either take all of its energy from the national grid or install an electrical generator of output 60 megawatts driven by a gas turbine of efficiency 36% as part of a combined heat and power or CHP scheme. The hot exhaust gases from the turbine are used to produce steam at high temperature and pressure for heating. The owners of the paper mill are considering the CHP option. Explain with reference to the data above and any other factors the advice you would give them. In your answer, you should firstly, explain why the maximum theoretical efficiency of a heat engine is much less than 100%. And secondly, use the information above, including the numerical data, to compare the two options. So in answer to this question, we need to address these 2 bullet points. Let's do them one by one. So let's first of all talk about the maximum theoretical efficiency being much less than 100%. So the first thing that we can say is that all heat engines have to obey the second law of thermodynamics. Now, instead of defining what this is, we can include this as a separate point. So there needs to be a sink to which energy is sent out. The next thing that we can write down is the maximum efficiency of such a heat engine. So we have TH minus TC over TH. So if I just give that some labels. So we've got the temperature of the cold region and the temperature of the hot region. Both of those need to be in Kelvin. Now looking at this equation, if the efficiency was at 100%, the top of the fraction would need to be equal to the bottom of the fraction. So TH minus TC would have to be equal to TH. Now cancelling the TH's off of this, that would then mean that TC would be 0 Kelvin. Now this wouldn't be possible, that's why it's a theoretical efficiency. But the other thing to consider is that there would be friction in the heat engine, which would mean unwanted energy loss. And the way that energy would be lost from incomplete combustion would be that the products of that reaction would be released with some of the chemical potential energy that could have been taken if the combustion were complete. So let's now move on to the second point. So we're now using the numerical data to compare the two options. Let's have a look at the numerical data. So we can see that with 60 megawatts, we can cover the energy requirements for the electrical components like the motors and the office equipment, but not for the heating requirements. And we can write that down. Let's look at the data again. So the electrical requirements sum to 57 megawatts. So we can calculate what the input energy would be if the output is 57 at 36% efficiency. So the input would need to be 158 megawatts. Now, if we're saying that 57 of those megawatts are going to be what we could call useful for the electrical aspect, the rest of the energy or the rest of the power that's going away as heat, which we would normally say is the wasted energy, could then be used for heating The problem is that it won't be enough, and that's going to be our next point, is that 101 megawatts is not enough to meet the heating requirements. So if we go back to our data, so we can say here that at least 34 megawatts will need to come from the national grid. If we're dealing with 57 megawatts here, then that will just be 40 because we're subtracting 101 from 141. But actually, if we're going to use the full output of this electrical generator of 60 megawatts, then redoing that calculation that we've just done, we'd be able to provide 107 megawatts for heating. And in that case, there would be 34 megawatts still needed from the national grid. Now, you don't need to make this calculation for a second time with 60 megawatts instead of 57, but you do need to write that as a point in your answer. So summing all of these power values together, we'd need a total power of 198 megawatts. So if we take all of the energy straight from the national grid, we can only do this at 40% efficiency. So the energy that we would need to take in the first place is going to be much larger by a factor of 2.5. So we would really need 495 megawatts in order to give 198 megawatts to the national grid. Remember that the efficiency of the power stations is up to 40%. So let's write that point down as well. So you can see there that 495 megawatts that we would need to put in. So we're dividing 198 by 0.4 to get that value, because 0.4 is the efficiency written as a decimal. So the benefit of this generator is that energy that would otherwise be wasted is used. So there's definitely a preference to use this combined heat and power scheme. And making this conclusion will complete your answer to this question. And then we can conclude by saying that this system is better than taking energy directly from the national grid. And that completes your answer. So in terms of marks for this question, the mark scheme states you need to have answered both bullet points with 8 or more relevant points. And they've included a list in that mark scheme, which I definitely recommend taking a look at. The points need to be evenly spread across those 2 bullet points, so you can't just put everything into 1 point. There aren't actually enough points to do that and have 8 points. You need to have referenced the data, which you can see we've done in our answer to the second bullet point, and you must also have come to a conclusion, which we've included here. There's also a mark available for quality of written communication, and it's points like that which mean that it's not as simple as having 1 mark per point in this question. There's also the fact that there's only 6 marks, and you need to have at least 8 points. It doesn't quite line up, but I would definitely recommend taking a look at the mark scheme to see how this is marked.